Imagine finding out that, well, the biggest, most dangerous storms in our solar system, these like billion-ton clouds of magnetic plasma flying toward Earth, have been essentially invisible to us for uh, 80% of their journey.
Yeah, it's a staggering thought, really.
I mean, we've basically been bracing for impact with our eyes closed this whole time.
Right. And, when you look at terrestrial weather down here on Earth, we expect incredible precision. We want to know exactly what hour the rain is going to start.
Oh, exactly. If my weather app is off by 10 minutes, I'm annoyed.
Exactly. But for decades in the realm of space weather, we were operating with a terrifyingly large blind spot.
Think about watching the local evening news, and the meteorologist steps up to the green screen to give you a hurricane forecast. They look right at the camera and say, well, there's a massive Category 5 storm headed exactly for our city.
And you're waiting for the time.
Right. And
Right.
then they say, when will it hit? Sometime between Tuesday morning and late Wednesday night, maybe Thursday. Good luck.
Yeah, you'd assume that meteorologist was completely out of their mind.
You would. But when you look away from Earth and look up toward the sun, that level of wild, almost comical uncertainty was, well, it was the absolute standard until very, very recently.
It really was. We were looking at events that could fundamentally disrupt modern civilization, and we were essentially just guessing when they might actually arrive.
Today, for you listening, we're going to explore exactly how humanity just conquered that massive blind spot.
It's such an exciting leap forward.
It really is. We are taking a deep dive into space weather, specifically coronal mass ejections or CMEs, and we've got a fantastic stack of sources for
A
this.
really diverse set of data, yeah.
Right. We're pulling from historical NASA mission logs, the official CCMC, that's the Community Coordinated Modeling Center, and their CME scoreboard data. Plus, we've got some recent academic papers on space weather forecasting and some really exciting news reports on a brand new orbital mission called PUNCH.
Which is just revolutionizing the field.
It absolutely is. So
Yeah.
our mission today is to figure out how the science of space weather just leaped from wild guesswork to pinpoint accuracy. Okay, let's unpack this. Because to really understand why predicting these storms is such a massive breakthrough, we kind of have to understand the monster we are dealing with, right?
Yeah, you have to know what a CME actually is.
Right. So let's start with the anatomy of a solar explosion.
Okay, so to picture a coronal mass ejection, you kind of need to abandon the idea of the sun as just, a static ball of light.
Like we draw in kindergarten.
Exactly. It's actually a boiling, roiling cauldron of plasma, and it's wrapped in these intensely complex, twisting magnetic fields.
And those fields are constantly shifting, right?
Yeah, they're always moving. And occasionally the tension in those magnetic fields builds up so much that it physically snaps.
Oh, wow.
Yeah, and when it does, a piece of the sun's outer atmosphere, the corona, physically erupts outward. It violently ejects this massive cloud of magnetized plasma into the vacuum of space.
And it's traveling at like thousands of miles per hour, right?
Yeah. Thousands. It is incredibly fast.
Which is just a mind-bending amount of mass and speed.
Yeah.
But reading through the research, it seems like the physical punch of that plasma hitting Earth isn't actually the main thing we're worried about.
No, not really.
The real danger is the magnetic payload it carries,
Mhm.
right? Specifically, this thing called the B's factor.
Yes, the B's factor is the crucial metric here. The B stands for the magnetic field itself, and the Z refers to the north-south directional axis.
Okay, got it.
So the interplanetary magnetic field, which is carried by the solar wind and these CMEs, it has a specific orientation. And the absolute most dangerous scenario for Earth is when the magnetic field inside that incoming CME is pointing south.
When it's pointing south.
Right. When that B's component is strongly negative.
I want to pause on that for a second because I would just assume, any massive magnetic field slamming into our planet is bad news.
You'd think so, yeah.
But the mission log specifically highlighted this southward orientation. Does that have to do with how Earth's own magnetic poles are set up?
You are hitting on the exact mechanism there. Earth has its own magnetic shield, the magnetosphere. And you can think of it as a giant dipole magnet.
Like one of those classic bar magnets you used in middle school science class.
Exactly, with a clear north and south pole. Now, what happens when you take two ordinary magnets and push their identical poles together?
They repel each other.
Right.
Like they physically push back.
Right. So if a solar storm hits Earth and its magnetic field is pointing north, so the same direction as ours, the fields clash and bounce off one another.
Oh, so our shield holds.
Our shield holds perfectly. But if that incoming CME has a southward pointing field, It is magnetically opposite to Earth's field.
Uh-oh.
Yeah. When they meet, instead of repelling, the magnetic field lines actually snap and connect with each other.
Wait, so it literally splices itself into our defensive shield.
That is the perfect way to describe it. In physics, we call it magnetic reconnection.
Magnetic reconnection.
Yeah, right. The incoming storm splices into our magnetosphere, effectively prying the front door open, and it creates this direct funnel. This allows immense amounts of solar energy and charged particles to just bypass our outer defenses entirely. They pour directly into our upper atmosphere and right down into our electrical infrastructure.
That makes a lot of sense.
Yeah.
But figuring out that orientation, like whether the storm is pointing north or south,
Yeah.
that seems to be a nightmare because space isn't just an empty vacuum.
It's definitely not.
Yeah, I was looking at a recent paper by Evangelos Piros and his team at Johns Hopkins, and they detailed this surprisingly intense storm from April 2023.
Oh, that was a fascinating case study.
Yeah, they had like 5 different spacecraft across the inner solar system tracking this one specific CME, and the storm did not behave the way they expected it to at all.
No, it behaved chaotically, and that's because of what it encountered on the way. Powers' team found that right near where the CME erupted on the sun, there was a large coronal hole.
A coronal hole.
Yeah, you can visualize a coronal hole as this region where the sun's magnetic field doesn't loop back down on itself, but instead it opens straight out into space.
Oh, wow.
This allows the solar wind to gush out at much, much higher speeds than the normal background wind.
And according to the paper, that fast solar wind acted almost like a jet stream in our own atmosphere, right?
Exactly like a jet stream.
It physically nudged this massive billion-ton CME off its original straight-line path, pushing it closer to Earth's orbital plane.
Yes, but not only did it nudge the trajectory, that uneven pressure from the solar wind current actually forced the CME to rotate as it traveled. It physically twisted the storm.
Wait, so a solar storm isn't just a straight cannonball? It can literally be steered and spun like a curveball by solar wind.
A spinning curveball that is expanding as it travels, yes.
That is wild.
And that rotation caused by the coronal hole is what turned the CME's magnetic fields opposite to Earth's, making that Biz factor strongly negative.
So it basically armed the storm.
Exactly. It locked that southward orientation into place, which severely intensified the resulting storm when it finally hit us. And this raises an important question, right?
How do you track it?
Exactly. How on earth do you track a twisting, turning, invisible magnetic curveball as it travels 150 million kilometers through the vastness of space?
Especially when you realize we couldn't actually see the curveball for most of its flight. Which brings us to the core problem of this deep dive, the tracking gap.
The infamous tracking gap.
We have established that these are dynamic evolving storms.
Yeah.
But for decades, we have been completely blind to them for the vast majority of their journey.
We refer to it as the 80% blind spot.
80%.
Yeah. Historically, our primary tools for watching these eruptions have been phenomenal. Legacy instruments like the SOHO spacecraft and the stereo observatories.
Right.
And they relied on instruments called coronagraphs. A coronagraph basically puts a physical disc over the camera lens to block out the blindingly bright face of the sun.
Because otherwise it just washes out the image entirely.
Exactly. And that block allows the camera to see the faint glowing plasma erupting around the edges.
But reading about these observatories, there's a massive inherent limitation to that technology.
A crippling limitation for forecasting, honestly. Because of how those cameras are designed and positioned, they could only clearly track a CME for about the first 20% of its journey toward Earth.
Only the first 20%.
Yeah. Once the CME traveled past that initial field of view, it became too diffuse to see against the background of space. It essentially vanished into the dark.
To build on that baseball analogy from earlier, instead of watching a high-speed video of a pitcher throwing a curveball, it's like we just had a blurry photograph of the ball just as it left the pitcher's fingers.
That's a great way to put it.
And based on that single photograph, forecasters had to guess exactly what time it was going to cross home plate.
They had no other choice. They took the initial speed, the initial size, and the trajectory of the CME in that first 20% window. Then they had to use mathematical models to guess how that plasma cloud would interact with the ambient solar wind in the dark, unobserved 80% of the trip.
And spoiler alert for you listening,
Yep.
The guesswork was incredibly rough.
Very.
I spent some time digging into the hard data from the CME scoreboard. And this was a massive analysis conducted by Pete Riley and his colleagues.
Oh, yes. The Riley paper.
They didn't just look at one or two recent storms. They looked at 6 entire years of forecast data. And they analyzed 32 different forecasting models from the brightest minds all over the world.
The CCMC is essential for our field. It serves as the ultimate proving ground. It's where researchers take their theoretical physics models and test them against real-world events to see what actually works.
Well, the results were genuinely shocking. Across 32 different models, over 6 years of data, the average error margin for predicting a CME's arrival was about 10 hours.
10 hours?
But the real kicker was the standard deviation. The standard deviation was 20 hours.
Yeah, that is huge.
Meaning a forecast could easily be almost a full day off. Even the absolute best, most sophisticated supercomputer models had an absolute error of 13 to 15 hours.
What's fascinating here is that this high error rate wasn't because the scientists were doing bad math.
Right, it wasn't a failure of intelligence.
Exactly. The science wasn't fundamentally flawed. The data was just fundamentally incomplete. You simply cannot model the complex fluid dynamics of a CME interacting with solar wind currents if you can't actually see it happening.
Because it's constantly changing.
Right. If you are asking a supercomputer to predict the precise arrival of a dynamic storm based on just the first few seconds of its launch, you are demanding the impossible.
And a 15-hour margin of error is, that's a lifetime when you're dealing with modern infrastructure.
That's completely unworkable.
Right. If you tell a power grid operator, hey, a massive electromagnetic storm is going to hit, and it will happen sometime between noon today and 3 a.m. tomorrow, they cannot work with that. You cannot shut down regional power grids or ground flights for 15 hours on a maybe.
No, the economic cost would be astronomical.
We desperately needed a way to turn the lights on in that 80% dark zone. And based on the recent news reports, NASA just found the light switch.
They absolutely did. They found it with a mission called PUNT. Yes, it stands for the Polarimeter to unify the corona and heliosphere. And it represents a completely paradigm-shifting approach to observing space weather.
Let's break down how PUNCH is actually built, because it is not just one giant space telescope like James Webb or Hubble.
No, it's very different.
It's a constellation. PUNCH consists of 4 small, suitcase-sized satellites placed in low Earth orbit. And for context, low Earth orbit is about 620 kilometers up, roughly the same neighborhood where the space station and Starlink satellites live.
Right.
What this constellation does from that vantage point is revolutionary. They are taking continuous 3D images of the inner solar system, capturing a new image every 4 minutes.
Every 4 minutes. And the old observatories had a very narrow field of view staring right at the sun. PNCH acts like a highly sensitive 3D wide-angle camera that covers a massive swath of the sky.
Okay, so it sees the whole path.
Exactly. By coordinating these 4 satellites, PUNCH allows scientists to track the cloud of plasma continuously. We no longer lose the CME after the first 20%.
That is incredible.
Every 4 minutes, we can watch the storm evolve in the deep space between the sun and Earth. We can see it twist, we can see the plasma clump together, and we can watch exactly how those hidden solar wind currents are pushing it around in real time.
And we finally have proof that this method actually works. This is the major breakthrough from the news reports.
Oh, the May storm.
Yes, on May 31st, 2025, the sun launched a major CME. And this storm was hauling. It was traveling at roughly 1,380 kilometers per second.
Very fast.
Under the old forecasting system, authorities were given a 12-hour arrival window. But scientists took the continuous 3D PUNCH imagery of that exact same storm, retroactively fed it into a computer model, and the results were stunning.
Because the model was receiving constant updates on the leading edge of the CME rather than just an initial starting speed, it was able to calculate the storm's evolving speed and geometry every step of the way.
Here's where it gets really interesting. With that continuous stream of PUNCH data, the scientists were able to predict the storm's arrival to within 30 minutes.
30 minutes?
They nailed a tiny window of 5 a.m. to 5:30 a.m. We went from a 12 to 15-hour guessing game down to 30 minutes.
It's just unbelievable.
I love how the principal investigator, Dr. Craig DeForest, phrased this in the reports. He said this leap in precision is the space weather equivalent of moving from steam engines to modern internal combustion engines.
It is an incredibly apt analogy for the transition we're witnessing. I mean, the steam engine was revolutionary because it proved we could harness mechanical power at all, just like early forecasting proved we could conceptually track solar storms.
Right, it was a start.
Exactly. But steam engines were bulky, inefficient, and lacked fine control. The internal combustion engine brought precision, dynamic responsiveness, and real-world reliability. Slashing the forecasting error margin down to 30 minutes gives us that precision. It changes the entire paradigm of how we defend against space weather.
That is exactly what I want to dig into next. We now have this shiny, highly precise internal combustion engine of solar forecasting. But for you, the listener, sitting at home, maybe commuting to work, or walking your dog, why does a 30-minute precision window actually matter to your daily life?
Well, it matters because a massive solar storm threatens the fundamental backbone of modern civilization, which is electricity.
Right.
When a severe geomagnetic storm hits Earth's magnetosphere, the rapidly shifting magnetic fields induce stray electrical currents in the ground itself.
In the actual ground.
Yes, these are called geomagnetically induced currents, and they seek the path of least resistance to travel, which just so happens to be our long-distance, high-voltage power lines.
And we know exactly what happens when those massive rogue currents hit the grid, because we have actually seen it happen. The infamous March 1989 superstorm completely knocked out the Hydro-Quebec power grid in Canada.
A total collapse.
6 million people lost power in a matter of seconds, and the entire grid was down for 9 hours. In a modern context, with our current reliance on digital infrastructure, a similar collapse would cost billions of dollars and pose a massive risk to public safety.
Absolutely. And to prevent that kind of catastrophic meltdown, power companies need to dynamically manage the load on their massive transformers.
Like turning things off or rerouting power.
Exactly. They have to shunt power around or temporarily disconnect vulnerable systems. But they cannot afford to take those preventative measures, which, cause their own economic disruptions, for a vague 15-hour window.
Because then the preventative measure is just as bad as the storm.
Exactly. A 30-minute warning, however, is highly actionable. Grid operators can brace the system precisely when the impact is imminent, drastically reducing the disruption to the public while saving the physical hardware.
It's the difference between telling a major city to board up their windows and shut down their businesses for a week just in case a hurricane hits, versus telling them the tornado will touch down at exactly 4/4 5 p.m.
You can actually act on the latter.
Exactly. Yeah. So it is not just the power grid we have to worry about. I was reading the research by Zhukong Kai from the University of Colorado Boulder regarding how these storms affect satellites, and it completely contradicted my intuition.
Oh, Kai's research is deeply fascinating because it highlights the secondary, often counterintuitive impacts of CMEs on our upper atmosphere, specifically a layer called the thermosphere.
For context, the thermosphere starts about 55 miles above our heads. It's the layer of the atmosphere where the auroras happen, and crucially where a lot of our low Earth orbit satellites operate.
Right.
Now, my intuition was that when a massive solar storm hits Earth, dumping vast amounts of intense energy and radiation into that layer, the atmosphere would heat up and expand outward, like a balloon.
That's what most people would think.
But Kai's paper, which looked at observations from NASA's Gold mission, showed that after a strong storm, the middle thermosphere actually cools down and contracts. I don't understand how dumping energy into a system makes it colder.
It sounds impossible until you look at the chemistry happening at that altitude. When that massive influx of solar energy hits the thermosphere, it breaks apart molecules and triggers a chain reaction that produces a vast amount of a specific chemical, nitric oxide.
Okay, so the energy is acting as a catalyst to create a new chemical.
Precisely. And nitric oxide is highly efficient at emitting infrared radiation. It essentially acts as a massive radiator for the upper atmosphere.
Oh, wow.
Yeah, so the solar storm dumps energy in, the atmosphere creates nitric oxide, and the nitric oxide immediately radiates that heat out into deep space. The layer dumps so much heat so quickly that it actually cools down relative to its pre-storm state.
And because cold things contract, the atmosphere literally deflates like a leaky tire. It shrinks away from the satellites operating up there.
Exactly. And when the atmosphere drops away, the atmospheric the friction that spacecraft are constantly fighting against to stay in orbit is suddenly drastically reduced.
Now, at first glance, less drag sounds like a good thing. Your satellite doesn't need to burn as much onboard fuel to maintain its orbit.
It seems like a bonus.
Right. But Kai points out the massive dark side to this atmospheric deflation. Space debris, dead satellites, spent rocket boosters, literal garbage floating in orbit also experiences less drag, meaning that junk stays up there significantly longer than any of our models predicted.
It throws off all the orbital decay calculations. In a densely packed orbital environment like we have today, satellite operators rely on a certain amount of a drag to naturally clear out the junk over time.
To kind of sweep it away.
Yes, and if the friction suddenly drops after a solar storm, objects aren't falling out of orbit and burning up when they are supposed to. This dramatically increases the risk of high-speed collisions in space, which could trigger a cascade of shrapnel.
So a solar storm hits, the upper atmosphere deflates to cool itself off, and suddenly we have an orbital traffic jam of space junk that just won't clear out.
If we connect this to the bigger picture, you can see why the precision of the PUNCH mission is just the beginning of a larger revolution.
Oh, absolutely.
Scientists are already taking this new capability, the continuous 3D tracking that eliminates the 80% blind spot, and they're feeding it into advanced machine learning algorithms. There is a new artificial intelligence model discussed in the journal Solar Physics called GeoCME.
So they're training AI on this new crystal clear tracking data.
Yes. By training AI on exactly how these storms evolve in that newly visible zone, they are learning to predict not just when the storm will hit, but exactly how geoeffective or destructive it will be upon arrival.
That's wild.
They will know the exact density, speed, and magnetic orientation before it even reaches our shield.
We aren't just predicting the arrival time, we're predicting the exact payload of that magnetic curveball long before it crosses home plate.
We are moving toward a future where we have a precise dynamic playbook. We will know exactly when to brace the power grid to prevent a blackout, when to tell astronauts on the space station to seek radiation shelter, and when to warn satellite operators that the drag in low Earth orbit is about to plummet.
So what does this all mean? It means humanity has officially closed the gap on the solar system's most dangerous blind spot.
We really have.
We went from staring at the first 20% of a solar storm's journey, making wild guesses about the rest with a terrifying 15-hour margin of error, to using the PNCH mission's continuous 3D imaging to nail down a 30-minute window of precision.
It's incredible.
The days of the space weather equivalent of a steam engine are truly over. We are entering a new era of heliophysics, where space weather is finally becoming as predictable and as actionable as a terrestrial hurricane.
It is a monumental achievement in both planetary defense and infrastructure protection.
It is. But it does leave you with a rather strange, lingering thought to mull over. Based on that thermosphere data we unpacked, if solar storms cause the atmosphere to deflate, reducing drag and leaving all that extra space debris floating up there much longer than expected, and we can now perfectly predict exactly when these storms will hit, will the next great era of space weather forecasting be less about protecting the electrical grid down here on Earth, and more about acting as an air traffic controller for a massive, high-speed traffic jam of orbital junk? Next time your local meteorologist tells you exactly when the rain is going to start, just look up and be glad we finally have that same precision for the sun.